Hello, members of the International Young Researchers Conference. My name is Seoyeon Kim, and I'm a student researcher at Daejeon Christian International School in South Korea. Today, I'll be presenting my research titled Visual Alerts for Toxic Gas Exposure. Real-time hydrogen sulfide detection in Korean public restrooms using colorimetric sensors. This project stems from my deep interest in sensor technology and its potential to solve real-world environmental and safety challenges in simple, accessible ways. In this study, I explored a low-cost portable gas detection method using lead acetate tape to sense hydrogen sulfide. The goal of my research was to evaluate whether this method could serve as a reliable, user-friendly approach to gas detection, one that could potentially be paired with digital systems to enhance real-time analysis, such as advanced auditory feedback. Here's a brief outline of today's presentation. I'll begin with the scientific background and method, followed by a side experiment, field testing, and the results. I'll also summarize key conclusions addressing the limitations and future directions. Gases often lurk unseen in our surroundings. Some, like hydrogen sulfide, are especially dangerous. They're colorless and, at high concentrations, even odorless, making them completely undetectable by human senses. This deceptive invisibility becomes deadly in enclosed or poorly ventilated spaces, where toxic gases can silently accumulate. A heartbreaking tragedy occurred in July 2019 in Busan, Minlak Town, South Korea. Hydrogen sulfide, or H2S, built up inside an underground public restroom at the Minlak Town building, where the ventilation had only been running for an hour per day. A high school student entered the restroom, inhaled the toxic fumes of H2S, and suffered severe brain damage before eventually losing her life. At that moment, she was exposed to over 1,000 parts per million of H2S, more than 60 times the occupational safety and health limit. This wasn't just an unfortunate accident. It was a clear failure of detection and prevention. It highlighted the urgent need for simple, accessible tools to identify toxic gases before they become deadly. This is a screenshot from a Channel A news report covering the Minlak Town tragedy. It shows governmental data from 2014 to 2018 on summertime asphyxiation accidents in South Korea. Out of the 24 total cases reported during those years, 14 were caused by hydrogen sulfide poisoning. These incidents occurred in places like sewage systems, wastewater treatment sites, or decaying sludge, spaces where toxic gases naturally form through decomposition. And yet, even with this clear trend, public awareness and preventive measures remained dangerously low, until tragedies like Minlak forced the citizens to pay attention. Toxic gas exposure is also a major issue in industrial settings. Former Samsung laborers reported frequent gas leaks at semiconductor plants, yet only engineers were notified, while workers received no proper alerts. Many worked in high-risk lines and unknowingly inhaled hazardous fumes from unknown chemical reactions. So, what is the culprit behind all these incidents? Hydrogen sulfide, or H2S, is a colorless, flammable gas that is highly toxic even at low concentrations. At low levels, it has a strong, rotten egg smell, but at higher, dangerous concentrations, it becomes completely odorless, which can mislead people into thinking the air is safe when it is actually not. Moreover, because H2S is heavier than air, it tends to sink and accumulate in low-lying confined spaces like underground restrooms. Just a few breaths can cause paralysis, seizures, loss of consciousness, or even death, as tragically seen in the Minlak Town case. Since human senses cannot reliably detect H2S once its smell fades, developing an innovative sensor that provides a clear visual alert for the presence of H2S is crucial for safety and prevention. This chart shows the health effects and increasing risk of death as hydrogen sulfide concentration rises. As you can see, once the odor disappears at around 100 ppm, people lose their natural warning system, which is why early detection technology of even small increases in H2S concentration is so crucial. For my experiment, lead acetate test paper by Sigma Aldrich was used as the sensing material. It shows a visible color change within 1 minute when exposed to hydrogen sulfide, providing a quick qualitative indication of its presence. The tape works with both gas and liquid samples and costs approximately $77 for 3 rolls, each 4.8 meters long, making it a relatively low-cost option for portable gas detection. Before conducting my main experiment in public restrooms across South Korea, I carried out a small-scale side experiment to further validate the reaction mechanism of the lead acetate tape. I placed a cooled boiled egg into a sealed container along with a strip of lead acetate tape. As the egg decomposed, it released hydrogen sulfide, a common byproduct of proteins breakdown. After 5 days, the white tape had turned brown, confirming the presence of H2S and demonstrating the tape's ability to react and provide a visible warning even under everyday conditions. This side experiment supports the reliability of lead acetate tape as a passive hydrogen sulfide detector. The field testing was conducted in public restrooms where hydrogen sulfide buildup is more likely due to frequent use and poor ventilation. I identified potential high-risk sites and selected 5 locations with varying conditions, including Seoyeon Rest Stop, Notobar Natural Camping Site, Namcheon Park, and Porame Park. At each restroom, I placed lead acetate sensor strips near toilets, drains, and corners, areas where gases tend to accumulate. The strips were left in place for 7 days, after which I checked for any color changes indicating the presence of hydrogen sulfide. After 1 week of exposure in all 5 public restrooms, no color change was observed on any of the lead acetate strips. All strips remained white, suggesting that hydrogen sulfide levels were below the detection limit of the tape at these sites during the test period. In conclusion, no significant hydrogen sulfide accumulation was found in the restrooms I tested, likely due to good ventilation and strong infrastructure in South Korea. However, many parts of the world still face challenges with poor restroom hygiene and ventilation. Therefore, simple and affordable detection tools like lead acetate tape strips could provide effective early warnings in these high-risk environments globally. While this study gave useful insights, there are still limitations. The number of test sites was small, and each was only monitored for 1 week. Furthermore, hydrogen sulfide levels can change with time of day, season, and other factors, so a longer, broader study is needed. Future research could and should include more locations and longer monitoring periods to capture these variations and better assess risks. This will help develop more effective detection and prevention strategies worldwide. Thank you very much for taking the time to listen to my presentation. If you have any questions, please feel free to contact me at my personal email. Bye!